Hi everyone, we will solve GATE 2017 Aerospace Engineering question number 8. A D level nozzle is to be designed for an exit Mach number of 1.5. The reservoir conditions are given as P naught equal to 1 atmosphere gauge, T naught equal to 20 degrees Celsius, gamma equal to 1.4. Assuming soft free flow in the nozzle, the exit absolute pressure in ATM is in 3 decimal places. This problem is from nozzle. So for knowing about flow in the nozzle, you can refer to this video lecture by Professor B. Babu from Department of Mechanical Engineering, IIT Madras. First, we will see what happens to the flow in converging and diverging duct. If flow is subsonic, then flow velocity will increase in the converging duct and it will decrease in the diverging duct. And if flow is supersonic, then flow velocity will increase in the diverging duct and decrease in the converging duct. It is the opposite of subsonic. So now we will see what happens in the converging diverging duct. So this is the converging diverging duct. If flow is subsonic here, then due to this converging part, flow will reach till Mach number equal to 1. If there is sufficient area change, then it will reach till Mach number equal to 1. Then after that, if in the diverging area, flow will increase till supersonic Mach number. For the opposite case, if there is supersonic flow, then it will decrease till Mach number equal to 1 in the converging part, then in the diverging part it will decrease further to subsonic number. Now we will see what happens if there are different pressure conditions at the nozzle entry and exit. So if we fix nozzle entry stagnation pressure, then we will see what happens if we decrease nozzle exit pressure, which is back pressure. So initially both pressure are equal. So if we start decreasing the back pressure, then flow velocity will increase till the throat. After that it will start decreasing, and as we decrease more and more pressure, it will increase till the throat and then will decrease. So for this case, mass flow rate will increase and our throat Mach number will be less than 1 because we have not reached the point till which this Mach number is becoming 1, and the exit pressure will be equal to the back pressure. And as there is no shock wave, so there will be isentropic flow. So now when our back pressure is such that at the throat Mach number is 1, and just after that flow velocity will decrease in the diverging part. So this point is called first critical point, and in this one flow will be subsonic. Only at the throat it will be Mach number equal to 1. So at this Mach number equal to 1, this throat achieve the critical condition. So this area at that time is called critical area, and Mach number at exit will be less than 1 this case, and mass flow rate will be maximum at that time, and back pressure will be equal to exit pressure, and flow will be isentropic, and this condition will be corresponding to exit Mach number will be corresponding to this area ratio AE upon A star, where A is the area of this exit, nozzle exit, and A star is the throat area at Mach number equal to 1. So if we start, this is the first critical point. That is similar to third critical point, in which condition this flow will be, instead of subsonic in the divergent part, it will be the supersonic, and flow will be isentropic throughout, and it will be at much lower pressure, back pressure, and Mach number will be equal to 1 at the throat, and this critical area will be throat area. So at the exit, Mach number is greater than 1, and mass flow rate and this pressure distribution in the conversion part will be constant, and it is called correctly expanded nozzle. Back pressure is also, exit pressure is also equal to the back pressure. Exit pressure is the pressure at the nozzle exit plane. Flow will be isentropic throughout, and this solution will be corresponding to the area ratio AE by A star for and supersonic solution for that. Now we will see what happened for this first and third critical point. So in this case, if we decrease back pressure to more than this first critical point, then in the conversion part it will reach till Mach number equal to 1, and the divergent part it will increase first to some supersonic Mach number, then there will be shock wave which will reduce it to subsonic flow, and then the flow will come back to flow velocity will reduce more due to the divergent part, and it will happen till this shock wave, normal shock wave reaches at the exit. At that point is called second critical point. So that point is called second critical point when this Mach number is at this normal shock is at the exit. So mass flow rate and pressure distribution conversion part will be the same. Throat Mach number will be 1, and area at the throat is called critical area, and there are 2 Mach number at the exit. When there is normal shock at the exit, then there are 2 Mach number just before the exit and just after the exit. This will be the supersonic and this will be the subsonic. And this exit pressure will be equal to the back pressure. So flow will be isentropic through till this shock wave. After that, there will be, due to this, it will not be isentropic. It will be isentropic after that also. And in between the second critical point and first critical point, these will be the condition. This mass flow rate and pressure distribution conversion part will be constant, how much depend after the first critical point, no matter how much we reduce the pressure. And throat Mach number will be 1 always, and critical area will be equal to throat area. And exit area Mach number for this case will be less than 1 because there is shock inside. So this Mach number will always be less than 1, and exit pressure will be equal to back pressure. This flow is non-isentropic. Isentropic till here, but due to this shock, it will not be isentropic. And position of this shock will be such that this back pressure equal to exit pressure. Now, if we reduce pressure more than this second critical point, and it is between second critical point and this third critical point, then what happened that there will be oblique shock inside this. So what happened that at the throat Mach number 1 and exit Mach number here will be greater than 1 because there is no shock, and as pressure has reached till here, so we need to increase the pressure to reach our required value. So pressure can only increase through the oblique shock. So there will be oblique shock at the end. So our exit pressure will always be less than the back pressure. So flow is isentropic in the nozzle and non-isentropic outside the nozzle. And this condition is called overexpanded because at the exit pressure is less than this back pressure. Now if we reduce pressure further than this third critical point, then it is called under expanded, because pressure is, we have to reduce more pressure after this exit pressure, and flow will be isentropic within the nozzle and non-isentropic through outside the nozzle. So reducing the pressure can only be done through the expansion wave. So at the exit there will be expansion wave, and after that, due to the reflection and all, there will be oblique shock. Now we will solve the problem. So in the problem, it is given that here reservoir pressure is 1 atmosphere gauge. So absolute pressure will be 2 atmosphere. Exit Mach number is 1.5 and flow is shock free. And we have to find exit pressure. So if flow is shock free, then this is the supersonic flow with isentropic supersonic flow inside it, and this will be the third critical point. So as flow is isentropic, we can use the isentropic relation P0 by PE equal to 1 plus gamma minus 1 by 2 me square to the power gamma upon gamma minus 1. We will put the value 1 plus 1.4 minus 1 by 2 into 1.5 square, 1.4 upon 1.4 minus 1. We will put this value in the calculator, and on putting this value in the calculator, we will get this value as 3.67103. So what is the PE? PE will be P0 upon 3.67103. P0 is 2, so this will be 0.54481 atmosphere. So our answer will be till 3 decimal digit, it will be 0.545 atmosphere. This will be the answer. Thank you.